Good evening, everyone. My name is Sriram Kumar, and I'm a cosmologist working at IIT Madras. I'm part of the Center for Strings, Gravitation, and Cosmology, a newly instituted Center of Excellence at IIT Madras. And the Chandrasekhar Lectures is a new series of lectures organized by the center. Today, we'll be having the third lecture in the series. The first lecture was given by Professor Robert Brandenberger. The second was given by Professor Clifford Will. And today we have Professor Kandaswamy Subramanian to give the third lecture. It gives me great pleasure to introduce the speaker, Kandu, as he is popularly known. Kandu had completed his PhD at the Tata Institute of Fundamental Research, Mumbai. Thereafter, he had gone on to do a postdoctoral fellowship, initially at the University of Cambridge and then at the University of Sussex in the UK, before becoming a faculty member at the National Centre for Radio Astrophysics, Pune. Over the last decade and a half, Kandu has been a member of the faculty at the Inter-University Centre for Astronomy and Astrophysics. Presently, he is a distinguished professor and dean visitor academic programs at IUCAA. His research covers a wide range of topics in cosmology and astrophysics, largely focusing on cosmic magnetism. He has received the Birla Science Prize in Physics and is a fellow of the Indian Academy of Sciences and Indian National Science Academy. Kandu, over to you.
Well, thank you very much, Sriram. And it's, of course, a great pleasure for me to talk about give a Chandrasekhar lecture. I hope you can hear me, Sriram.
Absolutely, Kandu.
Yeah. So on magnetizing the universe, and this is absolutely one of my favorite topics. And I hope by the end of this hour, you're also as magnetized as me, and look forward to that. So it's great that Sriram caught hold of me because and it's an honor to give this lecture here. And I thank the organizing committee of this Chandrasekhar lecture and this center that has been started at IIT Chennai, and wish it all the best. Before I just start off diving into the topic, let me just say that it's been a great pleasure to work with this large number of people, at least on this particular topic. Several of them are my former PhD students. Some of them are very close collaborators. Some of them are very young collaborators. And for example, Leon Mestel and John Barrow, unfortunately, have passed away. And they were my original collaborators on this topic. So the basic message that I want to convey is that the universe is magnetized. We are, of course, sitting on a magnet. The Earth is a magnet with a North Pole and South Pole, and we kind of navigate ourselves using this magnetic field sometimes, at least. Now, of course, you have all the GPS, but in the olden days, we would have a compass to navigate ourselves. Not only the Earth, but several other planets in our solar system, the nearest star, the Sun, many other stars are all magnetized. The magnetic field of the Earth, which is where we got our first unit of magnetic field, is a Gauss. It's a fraction of a Gauss. The solar magnetic field can be like a Gauss to 1,000 Gauss at the sunspots. Then on top of that, even galaxies, which are, as you know, full of, let's say, 100 billion stars, have an interstellar medium, an ionized plasma, which also hosts a magnetic field of about a microgauss or so, or tens of microgauss. Not only our galaxy, but also nearby galaxies, and also galaxies at high redshifts, and even very big collections of galaxies called galaxy clusters on hundreds of kiloparsec scale. By the way, a parsec is about 3 light years. Our galaxy extent is about a few tens of kiloparsecs. And a galaxy cluster is 1 million a million parsec or a megaparsec, host magnetic fields. And perhaps even the intergalactic medium in regions devoid of galaxies. Not only they host magnetic fields, but they also host a magnetic field which is fairly coherent, as I will try to describe. And the basic question that comes is, how do such coherent magnetic fields arise in the universe? And that's the title that I've given, Magnetizing the Universe. So I will talk about things which are fairly, a language which is probably you're familiar with, called batteries and dynamos, but not in the context in which I will talk about the cosmic batteries and the cosmic dynamos. So I'll first begin to talk about batteries, which provide a very small magnetic fields from zero magnetic fields. Then I'll go on to discuss dynamos, which amplify this field from turbulence, from converting kinetic energy into magnetic energy, and types of dynamos which are called fluctuation dynamos, and things which order the field on scales much bigger than the scale of the stirring motions. Finally, I hope to have some time to discuss a topic which is a favorite of many people in the conference which is going on, inflation and inflationary magnetogenesis. There are two references I put here. One is a review which I wrote called From Seed Magnetic Fields to the Galactic Dynamo. And then another is a book that Anwar Shukurov and I recently put out, published by Cambridge University Press. You can, of course, get in touch with me if you want more references or different references. So let's just begin. It's possible to measure magnetic fields in something like a galaxy. And that always is an interesting question. How is it that a galaxy which is farther away from you, you can measure the field at all? And the basic idea that one uses is what is called the synchrotron radiation. So if you have a magnetic field, and that's denoted by this arrow here, and you have a relativistic electron, what happens is this relativistic electron experiences a Lorentz force, which is proportional to the velocity cross vector product of velocity and the magnetic field. So if it's moving in this direction, the force is in this direction, and it typically undergoes a helical orbit, as shown in this blue line. If it's a relativistic electron, it also beams its radiation in a narrow cone along the direction of the velocity. Okay, and if you calculate the electric field of this radiation, it turns out to be proportional to the acceleration vector. So just detecting synchrotron radiation in some way will show that there is relativistic electrons in magnetic fields. How do you make out synchrotron radiation from, say, black body spectrum? Because the radiation is beamed for highly relativistic charged particle, it's like a lighthouse which just goes across you every once in a while, even though there is a certain frequency of gyration about the magnetic field. The beaming is in a very narrow cone, which is inversely proportional to the amount of energy that it has. And for highly relativistic particle, you only see pulses. So the spectrum is spread over a wide range of frequencies. And from the characteristic of the spectrum, you can make out its synchrotron, or not some thermal emission of something else. So once you detect synchrotron emission, you can figure out how much is the density of relativistic electrons and how much is the density of magnetic fields in this. And by looking at the polarization of the synchrotron electron radiation, you can figure out that since it's proportional to the acceleration, the electric field, and the acceleration is perpendicular to the magnetic field direction, you will get the polarization perpendicular, and you will get the idea of the component of the magnetic field perpendicular to the line of sight. This is the line of sight, this is the magnetic field, and you will get a component perpendicular to that. You can also measure the component parallel to the line of sight by something called the Faraday rotation effect. That is, if you take linearly polarized radiation, which propagates through a magneto-ionic medium, it turns out that the left circular and the right circular polarizations propagate at a slightly different phase speeds. And when you take this linearly polarized radiation and it comes through here, when you superpose back on it, these 2 degrees of polarization, you get a different angle to the polarization. And that angle depends upon what's the component of the field parallel to the line of sight. So purely from measuring synchrotron radiation from a galaxy, you can work out the intensity of the magnetic field. You can work out its component perpendicular to your line of sight and a component parallel to your line of sight. So you can get a kind of with almost three-dimensional information about the structure of the field. And this has been done for many galaxies. For example, what is shown here is a galaxy called M51, which is a disk galaxy, which shows a spiral structure like this. And what is shown here is the optical light. Superposed on that are contours of synchrotron emission. And then these lines here indicate the direction of the magnetic field as projected perpendicular to a line of sight. Firstly, from measuring the synchrotron emission, you figure out that you have a few microgauss magnetic field. Now, this may seem small compared to the Earth's magnetic field, which is like a gauss, but it is spread over a distance of tens of kiloparsecs. So the energy contained, and as I said, a parsec is about 3 light years. Kiloparsec is 1,000 parsec, tens of kiloparsecs, and then the disk is thick, about a kiloparsec thickness. So if you take the volume, the amount of energy that it contains is tremendous amount of magnetic energy. Okay? And you can also see that these dashes have a certain level of coherence in them. And so it looks as if this magnetic field is kind of ordered on the scale of the whole galaxy. So you have evidence from these kind of radio observations for magnetic fields which are coherent on tens of kiloparsec scales, and also some random component to this magnetic field. Okay. And similar magnetic fields have also been inferred very early in the early universe at redshifts about 1 or something, or a few billion years back in look-back time from here to in the past.
Kandu, I'm sorry to interrupt. There is a brief question asking what is the difference between cyclotron and synchrotron from a student, I believe.
Fantastic. So if the particle is not relativistic, then you will still get a gyration like this. And the frequency of radiation that you get is related to a gyration frequency, and that's a cyclotron radiation. On the other hand, if a particle is relativistically moving, then the radiation is beamed in a narrow cone. So the time over which the radiation reaches you is a very narrow pulse in the overall period of the orbit. And if you take the Fourier transform of such a narrow pulse, you'll get a whole spread of frequencies. And that spread has got many of these cyclotron things spread over, or gamma squared times, where gamma is a relativistic factor for the student, times the cyclotron frequency, and that is synchrotron radiation. Hope that's clear now. So just like our galaxy, there are galaxy clusters, for example. Now here the scale is 500 kiloparsec. So this is a galaxy cluster, which has this strange name, RXC, whatever J, this thing is detected by the Chandra X-ray observatory. Again, Chandrasekhar's name is attached to this particular X-ray telescope. And what you see here is, in color, is the X-ray emission from this galaxy cluster. What it indicates is that this whole cluster is full of very hot gas emitting X-rays. What you see in the contours here, if you can see, is the radio contours as measured by our own GMRT in Narayan Kaur near Pune at radio frequencies of 235 megahertz. And it shows, and this radiation, this giant radio halo which occupies the whole cluster, also indicates magnetic fields and cosmic ray electrons in this, filling this cluster. And you can also go and measure Faraday rotation behind a whole bunch of clusters. And you'll find that there's an excess of Faraday rotation. What is plotted here is Faraday rotation as a function of the impact parameter from the center of the cluster, of a galaxy cluster. What it shows is that as you go near the centers of clusters, like 1,000 kiloparsec and smaller, you get an excess of Faraday rotation. And that shows statistically. You also have magnetic field which are ordered. And if you ask how ordered it is, it's also about tens of kiloparsec. So the strength of the magnetic field is again few microgauss. The coherence scale is tens of kiloparsec, but it's not as coherent as the previous galactic field. It is actually a random field, which you can see which is kind of producing both positive and negative kind of Faraday rotation. For the cosmologists who have seen the microwave background radiation, and they are all the time thinking about interpreting the microwave background radiation, for an astronomer, what is equally interesting is this picture from the Planck satellite, which shows the dust emission at very high frequencies, which what you see in all this textured stuff here is the direction of the magnetic field, which is inferred from the polarization of this dust emission. In fact, one of the earliest papers to estimate the strength of the magnetic field in our galaxy is due to Chandrasekhar and Fermi in 1953, because one of the earliest indications was not radio astronomical observations, but starlight which is scattered by dust grains. The dust is elongated and it's kind of with its minor axis aligned to the magnetic field. And more light is scattered along the long axis compared to the short axis. And so you get a sense of the direction of the magnetic field from the scattered light. And there's a spread of directions, which is about 20 degrees or so. What Chandrasekhar and Fermi argued is that if this magnetic field is turbulent, and it's in some kind of being stirred up by the interstellar medium, which is also turbulent, then if you know the velocity in the interstellar medium by some kind of equipartition energy argument, you'll figure out the strength of the magnetic field from just the scattering. And they inferred a magnetic field strength of about 6 microgauss from this argument, which is not very far away from what you infer today. So this is 1953, Chandrasekhar. Of course.
Chandu, yes. There is another question asking, how do you determine the coherence length?
Oh, in this particular case, you can see everything is aligned along the disk of the galaxy. In this particular case, you have to take both the Faraday rotation and the polarization and make a model of it. What you will find is that there's a large-scale axisymmetric magnetic field. You can see on the whole thing is wrapped around the disk of the galaxy. You'll also infer that there's a random component to the magnetic field. Unlike the Earth, which you will see very nice ordered dipole, more or less. In galaxies, the random component, as I've said here, is actually larger by a factor of few. So if you went to the compass, the random component will wander around every 100 parsecs or so. This length scale is the coherence scale of the random field. The whole galaxy length scale is roughly the coherence scale of the ordered field. Okay? I hope that answered that question. Oh, I go ulta all the time. Right. So similar infrared observations can also be made of the same galaxy. This is a radio image, and there's the same galaxy in infrared polarization. And now the radio astronomers have learned how to draw these nice textured diagrams from the CMB people. And so you can see that there are very similar kind of characteristics from probes of the magnetic field from the synchrotron cosmic ray, electrons, the relativistic electrons, and from dust polarization in infrared. One of the reasons I'm showing this, I'm some nth author in this recent paper. So I just thought, as a theorist, I'm always proud to be some, very long list of authors, some nth author in an observational paper. So let's get down to how do we produce all these magnetic fields. Now, you may imagine that if you have a magnetic field which is structured, then you have a current. And we know that if you have a current in a wire, the current will decay because of resistance. And so the magnetic field will disappear. Okay? You can first ask, what is the decay time of magnetic fields? It turns out that in the Earth, the decay time is about 1,000 years or so. So if you did nothing to the Earth's magnetic field, then it will just simply vanish in 1,000 years. But we have observations from digging down, ice cores, all kinds of things, that the magnetic field has been around for, several millions of years. And in fact, it's even reversed various times in the Earth. Now, if the decay time is very long in galaxies, the basic reason is that you know that the magnetic field is structured on, let's say, 100 parsecs or kiloparsec type scale. The current associated with such a magnetic field is very weak because of the large length scales. If you're a physics student, you will know from Ampere's law that curl of the magnetic field is related to the current. So the current is B by some L, and that L is very large. And the dissipation depends upon the current squared, okay? Like I squared R for a wire. And so the amount of energy lost, if you calculate, turns out to take more than the age of the universe from galaxies or galaxy clusters, just because the length scale is large. But that doesn't mean that the field will stay forever. And that's basically because associated with every current, associated with the structured field, there's a current. Associated with that current and the field, there's a force. If you put a wire with carrying a current in a magnetic field, it will experience a force. That force will move the fluid. If the fluid moves and the fluid is viscous, then energy will be lost. If the fluid is not viscous, then something fantastic happens. It drives what is called turbulence. The energy gets transferred to smaller and smaller and smaller scales until the energy is lost. So magnetic fields just don't stay forever in all these systems. They have to be constantly maintained. So motions have to, because of this, you need some way of all the time maintaining magnetic fields. How do you maintain magnetic fields? For maintaining magnetic fields, you need a current. How do you get a current? You need some electric field. The way in which the magnetic field is maintained in all the astro systems that we know of is by just depending upon the Faraday's law of induction. If you're again a student of 12th standard physics, you would know that if you change the magnetic flux, you induce an electric field and current or something like that. We operate the other way around. If we have a curl to the electric field, we can change the magnetic flux. So how do you get a curl to the electric field? If you take Ohm's law, that the current is proportional to the electric field, but electric field in the rest frame of the plasma. So if you are sitting in a plasma quietly and you apply an electric field, you'll get a current proportional to that. That's Ohm's law. But if the plasma itself is moving, if the conductor is moving around, then the total Lorentz force is not just E, but also E plus V cross B times the charge. Because of that, your current is not proportional to just the electric field, but also V cross B by C. Now you write it the other way around. You write the electric field as minus V cross B by C plus J by conductivity. If this electric field has a curl, then you can change the magnetic field. So this is basically an inductive effect. In fact, in your cycle dynamo also, it's an induction. Of course, nowadays, young people don't drive a bicycle, which is where the lamp is lit by a dynamo. They ride with some LED lamp and all that. But in the olden days, maybe in my days, or even, I don't know, Sriram's days, if you have a bicycle and you have a lamp in that bicycle, and as you pedal, you have a magnet and you have a coil, and then your thing goes around and flux is constantly being changed. It induces an electric field. The electric field drives the current lights the lamp. The same process, very different, the same equation will be obeyed by the magnetic field. So given a particular amount of motion in the system, you can change the magnetic field. But of course, once you have the field, it also back reacts because you have the Lorentz force that we are talking about, the J cross B force. And so it changes the velocity field. So it's a very complicated and interesting system called magnetohydrodynamics. Chandrasekhar himself spent about a dozen years on this kind of study. If you have read about Chandrasekhar, he would go to a particular field, he will do a lot of work, he will write a book, and then he will move on to some other field. So during the 50s and about 60s, he spent time on studying MHD problems, magnetohydrodynamics problems, including, as I said, that work with Fermi, then the work on turbulence, then work on what is called the magnetorotational instability. So that's a different story. Given this equation, what you can show is that the magnetic flux, that is amount of magnetic field going through any particular unit area, through an area, is conserved. The magnetic field, so-called, is frozen into the fluid. So that this flux, B dot ds, if I define, does not change if your resistivity, by the way, this was the conductivity and this inverse of that is the resistivity, is very small. And this is the basics of all dynamos. That is, you move the fluid around, okay, magnetic flux is frozen, and somehow you transfer energy from velocity to the magnetic field. For example, I've shown you a picture of a tube of magnetic field, a flux tube, and I stretch this flux tube like this. So it has stretched, and because of, suppose I stretch it in a way in which you roughly conserve the volume of the tube because it's become longer, the area of cross-section has decreased. The same amount of flux is going through that because flux is conserved, B and A is constant. So the field strength has increased because B into A is constant, A has decreased, so B has increased. So what you have done is by just stretching this flux tube, transferred some energy into the field from the motion, okay? And this you can show is a direct consequence of just this induction and this curve, except that now I have used the fact that magnetic flux is frozen. In fact, it's a very, very important concept because once you have this concept of magnetic flux being frozen in plasma, you can simply picturize everything in terms of just what the field is doing as the plasma moves around. And that's a very nice way to picture everything. The importance of this, of course, resistance is important. Otherwise, you will never change the field topology. So again, you can measure the importance of this induction to dissipation, and that's a very, very large number, a dimensionless number called the magnetic Reynolds number. Okay, and so in most of the regions, flux is frozen, but the regions where flux is not frozen is absolutely crucial to change the magnetic field finally and to make irreversible changes to the magnetic field. Now, all this depended on induction, but induction means that you need a magnetic field to induce. But suppose you had zero magnetic field, and this is what we imagined that the universe started with, no magnetic field at all. Then how will everything work? So you need some initial field, and that's called the battery. And then you need a way of amplifying this field, and that's called a dynamo. Oh, I always go backward. So let's think about a battery. Suppose you had no magnetic fields in the universe. How would you ever get any field at all? Now, if the way to do this is, it depends. It turns out that, of course, I will later talk about inflation and way of doing it there. But in the normal plasma, there are many interesting ways of doing this. All of them crucially depend upon the fact that positive charges in the universe have different properties compared to negative charges. For example, just take hydrogen, and let's say you ionize the hydrogen. Your charge is the same, equal, because you have equal number of protons and electrons. But the electrons have a mass of 500,000 electron volt. The protons have a mass of 1 giga electron volt. So the ratio is about 2000 or so. Now, suppose I apply to this plasma a force, okay, on both these components. The electrons, suppose I apply the same force. For example, the force could be due to a gradient in the pressure in the plasma, in the fluid. That doesn't, pressure only depends on the number of particles. It doesn't depend upon the mass of the particle. Now, apply this force. The electrons feel the same force as the protons, but they are very much less massive. So they will accelerate. The protons, lazy guys, they will come behind them, try to come. But electrons cannot accelerate away. There will be too much charge separation. An electric field will build up. The electric field can be estimated by balancing the force due to the pressure, the gradient of the pressure, with the force due to the electric field. The charge density is the charge, N is the electron density, the electric field that you want to estimate. I equate these two, and I get this electric field. Such an electric field exists in our atmosphere also. Now, suppose this electric field has a curl. Then from Faraday's law of induction, your magnetic field can change. This is how a battery works. If I take a curl of this, for example, now curl of gradient is always zero. But there can be a term which is gradient of n times cross gradient of the pressure. I've just written the pressure in terms of density, temperature, and all that. This battery was invented by Peter Biermann again in the 50s, that's why I've called it the Biermann battery. He applied it to trying to produce ab initio magnetic fields in stellar interiors, because a star is rotating, pressure gradients and density gradients are not always parallel to each other, and you can produce some field. We applied it again long back now, 94 and now 2020, whatever, 2, to what I call when the universe gets reionized, then there are sources of ionizing photons, okay, which are trying to ionize its medium. And there's a temperature gradient across that ionization front. There are things which are going to form galaxies, collapse to form galaxies. There are density gradients there. The source is some quasar in some galaxy. The density is some other galaxy. These two gradients have nothing to do with each other. They can be having a cross product. They're not parallel. So that induces a curl to this electric field, induces a magnetic field for the time in which the ionization front passes that region. So you calculate how much field you get about 10 to the minus 19 Gauss. You can also apply it, for example, in curved shocks which form in structure formation. Then it turns out you generate again such non-parallel density and pressure gradients. Net effect is that this induction equation, you can get magnetic field not only from this inductive effect, the dynamo thing, but also due to such source term, it doesn't depend on the field at all. So it's like having a battery. You have a wire with no current. You want to produce a current, you connect it to a battery. The battery doesn't depend on the field or the current. It's just trying to produce a potential difference, can be a chemical effect. Here it's a thermal effect. Such batteries can produce the first fields in the universe. And they will always be there. They will be there in the first stars. They'll be there in the first accretion disks, in the first galaxies which form during reionization, during structure formation. But it turns out all the battery effects that people have talked about and thought about produce fields of this order, 10 to the minus 19, minus 20 Gauss. We see in galaxies micro Gauss or tens of micro Gauss. No way these batteries will explain that. Later I will talk about the intergalactic medium fields. That's also maybe 10 to the minus 16 Gauss. The batteries also don't explain that. So you need some way of amplifying the field. And that's where dynamos come in. And you need some way of dynamo amplification of the field. The simplest dynamos, I always go backwards, okay. This is a simulation which shows such a battery. The simplest dynamo is called a fluctuation or a small scale dynamo. And it relies on a very, very universal fact in all these systems that we are thinking about, like stars, galaxies, galaxy clusters, even the Earth's molten core, that there are random motions in the system. Now, why is the star got a random motion? Many stars, like our sun, has boiling, a region which is boiling. Convection, it's called, okay? Why does a galaxy have random motions? Because there are stars, massive stars, which explode as supernovae in the galaxy. And you have all these explosions going on in the galactic interstellar medium, which push the gas around randomly. Galaxy clusters, they form by many objects like galaxies and smaller mass objects merging together. And as they merge, they stir the medium and induce random motions. So all these media, the Earth's molten core, as the core solidifies slowly, it releases latent heat and drives some small scale motions in the core, in the molten core of the Earth's interior. All of them have some kind of random motions, sometimes turbulence. This is very common in all these systems. Given turbulence, given random motions, those flux tubes which I was showing you, which are getting stretched and field getting amplified, that kind of thing will be very generic. Why? Because if you think about a random walk, if you are a person who is, hopefully don't do this, get highly drunk, and you are starting from some place, you know that there's a probability as you randomly walk, you'll walk far away from the initial place. Of course, the probability distribution will still have a mean, which is the place you start, but the dispersion will increase with time. So if I put some random fields into this turbulent medium, which has got all these flux, magnetic flux, any two ends of this field will just move away from each other statistically, just by random walking in this random motion. And so typically these field lines will get stretched and they will get squeezed in the perpendicular direction and the field will get amplified. Okay, so very generically, in turbulent systems, you will produce from, where does the energy come from? The energy is coming from this kinetic energy of random motion. Once the field becomes very strong, it will resist this stretching. The stretching could be just pulling this rope of flux tube. It will resist that. It will try to spring back the Lorentz force. And so you will saturate the dynamo. So this is a very simple and very generic dynamo in all systems that you have, in galaxies, in stars. It's called the fluctuation dynamo because it depends on the random motion that you have. Small scale dynamo, because it doesn't produce coherent fields more than the scale of the stirring that you have. That is, if I'm going to stretch this flux tube coherently over some scale, that's the scale of the field also, okay? Until very small scales. Now, what is that scale? For example, in galaxies, it is the scale of the largest supernova remnants that you have, which will be tens of parsec scale. Whereas we said the field is coherent on kiloparsec scales. So this is a very good way of generating fields in things like galaxy clusters and the random field in stars, but not a good way of generating magnetic fields which are coherent on the scale of the whole galaxy, or which have this very orderly field, like, for example, even in our Earth, the dipolar field, or in the sun, which has got a very regular oscillation over a 11-year kind of cycle period. Also, as you will notice, that this field comes at a cost because you're always squeezing these flux tubes, perpendicular direction. So the field is likely to become highly intermittent. For example, there is a simulation by Pallavi Bhatt, who did it during her PhD times. And so what she did was, and now she's a faculty at ICTS TFR in Bangalore, so you should catch her for all these simulations. I'm an observer of numerical simulation. I never do all these things, but luckily I got a whole bunch of very bright young people who worked with me and did all these things, kind of work. So what she has done here is taken a box, periodic box, put a seed magnetic field and stirred it on the scale of the box. And what is shown in the left-hand side is the magnetic energy per wave number. Wave number is inverse of the wavelength. Larger the wave number, smaller the length scale, wavelength. This is the whole scale of the box. And you see initially all the energy is on small length scales. It grows, it increases and saturates in a more coherent fashion. But this is the stirring scale of the box. So in her simulation, you will see that the field has grown, but it is highly intermittent in nature. It is strong in some places, empty in some places. What is shown here is the Z component of the field. In the Z, in the three faces that you can see of this periodic box, you can see strong field region, but a lot of region is red, which is almost zero kind of field. So such a kind of small scale dynamo generates random fields very easily. It would generate even the Faraday rotation that sometimes you can observe in the galaxy cluster, where even though the field is very intermittent, because the Faraday rotation involves an integration, that makes the signal more coherent because you're summing up, you're sampling the whole C that you have, very weak C. But it's actually not great for explaining galactic ordered magnetic fields. Now, of course, you will see that I have written more on my slides than what I'm saying. Please just listen to what I'm saying. Don't worry too much about what I've written. If you go back to these talks, the recording, you can read what I've written also. So there's still an open problem how this whole saturation occurs because models, analytic models, which are called closure models, are approximate. Simulations are limited to modest Reynolds numbers, maybe 1,000 or 2,000 of this dimensionless number that I mentioned, whereas I was mentioning numbers like 10 to the 19. Okay, so we have a long way to go. A lot of young people, it'll be good for them to get excited about such problems. Also, something very remarkable happens if the turbulence has a property called helicity. Now, you know what? You probably have encountered what is helicity because all of us have done at some stage or the other a screw, tightened a screw or loosened a screw in something. If you look at the threading of that screw, that's a helix. Or the picture which I showed you of an electron moving in a helix. So it moves round and it also moves in some either up or down. Okay. It turns out that if you take the same periodic box, and these are simulations going back to 2001 by Axel Brandenberger, now you stir it in a helical way. That is, you put these screw-like motions randomly everywhere, but with the same sense of the screw, either a right-handed screw or a left-handed screw, randomly. Here the fluid is being stirred at 1/15 the scale of this box. So these chota regions that you see here, that's the scale of the stirring. And you watch this system. If the turbulence had no helicity, then you get back whatever I showed you, the picture which Pallavi had. Once the system has helicity, it remarkably orders itself to a field configuration. Here it's just a single sine wave across the box, which has got a coherent scale. Here 15 times longer, bigger than the scale of the study. So this is very remarkable always, that when you do something on some small scale, you get an order on a much bigger scale. That's always very amazing to understand. How is it that you get such order out of such chaos? Okay, this happens if you have helicity. How do you understand such a thing? I thought I will give you a little flavor of the maths, but if you are not happy with maths, please forgive this particular slide. Suppose you have a velocity and a magnetic field, and you break it up into both an ordered mean field and a fluctuating field. The induction which you had, which was V cross B, will now have four terms: V bar times B bar, chota v times B bar, V bar times small b, and then you average this equation. Then the mean field or the large scale field satisfies an averaged equation, where of course this V bar cross B bar will be there. Average of V will be 0, so V cross B bar will average to 0. V bar cross chota b will average to 0. But the quadratic in small scale, small v times B average, this one, need not be 0 because they could be correlated. In fact, even if they were not initially correlated, what this math shows, and I don't want to get into it, is that because the velocity field is stirring the system and changing the magnetic field. In particular, if I look at the small scale magnetic field can also be produced by the tangling of the mean magnetic field by the small scale motions. The small scale magnetic field and the small scale velocity field can get correlated. And they can produce an electric field which is proportional to the original magnetic field, which is amazing because then what you will have, where is this? Yep. then what you will have is this induction equation, but it has an extra term where you have an electric field which was which was proportional to the original magnetic field. And if you work out the maths, how does this electric field gets created? The electric field depends upon exactly this helicity in the random motions. So these helical motions can create an electric field which is parallel to the original magnetic field. Now, induction, as I said, is V cross B type term. If velocity is parallel to B, you will have zero. But here the turbulent velocity is inducing on a mean magnetic field to produce something parallel to the mean magnetic field. So it's also very counterintuitive in this sense. Now, forget the maths. If you want to look at it in terms of pictures, suppose you have a magnetic field in the disk of a galaxy, which is wound up like this, a toroidal component of the magnetic field. And you have helical motions in the system. Then the field is, let's say, frozen into the fluid. So what a helical motion does is to firstly lift, you have these small helices going on. So you will first produce a chota omega like this, okay, because of the upward motion. But helical motion also involves a twist. So when you twist this small omega, you'll get a loop like this. That loop has got a component of the field which is now in the radial direction, if you merge all those loops together. In galaxies, the central part of galaxies are rotating faster than the outer parts of the galaxy. So if our sun is going once around every few times 10 to the 8 years around the center of our galaxy, the central regions may be going around in 10 to the 8 years or even smaller. If I have a radial component of the magnetic field and the field is frozen into the plasma, it's like stirring cream in a coffee cup. You will elongate that cream and you'll freeze that cream and you'll produce a wound up bit of cream. And so you'll get a phi component of the magnetic field from the radial components just by differential rotations. So differential rotation generates B phi from BR. Helical motions generate BR from B phi. You couple these two together, you have a dynamo which produces large-scale fields like this.
Kandu, you have about 15 minutes.
15 minutes before questions or 15 minutes?
Before questions.
Okay, great. Fine. Thank you, Sira. So this is how our galaxy is taught to produce large-scale magnetic fields. Okay? Of course, this simulation did not have such, I always get lost. It didn't have that shear. Just pure helical motions itself will do because they produce an electric field parallel to the original magnetic field. If you have an electric field parallel to the original magnetic field, you have a curl, you have a current, which is going that way, you have a current going along the field, so you have more fields produced perpendicular to it. So you have more current going perpendicular, that produces more field parallel. So you couple these two things. Pure helical motions itself is enough. But in galaxies, you're also aided by the fact that the galaxy is differentially rotated. Of course, you can also ask, in a system like galaxy, how do you produce helices? And it is a very similar question as to why cyclones happen in our Earth's atmosphere. Turns out that in any rotating stratified system, for example, suppose you have something rotating and pressure is decreasing up like this, you take a parcel of gas and it rises, it expands because of stratification. When it expands, it has to conserve angular momentum. So it twists in the inertial frame. If you go to rotating frame, there's a Coriolis force, which twists it. So the motion is up and twists. That's a helix. That's how cyclones are produced. That's how helical motions are produced. Now, you may think if I go down, I will cancel the effect. In fact, you add the effect because you go down you contract, velocity direction is changed, you conserve angular momentum, you twist in the opposite direction. Going down, twisting like this, going up and twisting the other way are both the same sense of the helix. So you'll get helicity in any rotating stratified system. Happens in planets, happens in stars, happens in our galaxy. Clusters of galaxies are not rotating very rapidly. You don't get such helical motions there. And so you are having to live on the fluctuation dynamo in galaxy clusters. Okay, I won't go into, there are very interesting problems to do with magnetic helicity conservation and all this. I will not get into it. Let me get into the last 10 minutes about the other stuff which I wanted to briefly discuss. So what you can produce from the small scale turbulent dynamos is magnetic fields in all these. There's a simulation of a big region of the universe called the Millennium Simulation long back. Nishikant here in the audience is an expert on these simulations. And you see all this, what is called the cosmic web. There's a rich cluster of galaxies, there's 100 megaparsec. So there's a cluster, all these little dots are galaxies. And in all of them, you can have turbulence and you can produce magnetic fields. If they're rotating, you will eventually be able to produce large-scale fields, although there are a lot of problems which I glossed over. But what about these regions which don't have anything? Naively, the only way you can get field into those regions is things outflow from these structures. And you can calculate that it's not extremely efficient. Of course, it depends on what outflow and what day of the week you're asking me this question. Okay? But it's not that efficient. And also, even if things go out, they will not be ordered so well. It turned out that you have some evidence, potential evidence, from gamma ray astronomy, that there could be magnetic fields in these void regions. And so let me take a few minutes for this. So the observation is the following. You have a distant, very active galactic nuclei, which people call a blazar, that emits radiation in very high energy. In this particular case, tens of tera electron volts. An electron volt, tera electron volt is 10 to the 12 electron volts. Okay. This radiation is beamed towards us, and that's how we see this blazar. Okay, it's coming towards us. Now, in the intergalactic medium between galaxies, you think it's all empty. It has got very dilute gas. It also has photons, radiation from all the stars and galaxies that you have produced by that epoch. This is in a nearby universe. Okay. These photons have electron volt energy. There's a process whereby a photon-photon interacts to produce electron-positron pair. But you require at least the rest mass of the electron. That much energy you require. So you require these two photons, the geometric mean of their energies to be at least more than 500 million electron volt. This is 10 to the 12 or 10 to the 13 electron volts. It interacts with 1 electron volt photon. So square root of that is at least million. And so you can produce pairs, E plus E minus pairs, as indicated here. The cross section for this is small. So this process happens far away from this blazar. By the time this radiation has come to do this, it has come into the void regions. Now, another interesting thing can happen, that this energy that the E plus E minus pairs have is some fraction of the initial photon energy. So it's also very highly energetic. There is also, if you have heard cosmology talks, there's something called the cosmic microwave background radiation, which fills the space in the universe. That can scatter off these E plus E minus and do what is called inverse Compton scattering, gain energy from these electrons. And from microwave kind of frequencies, or 10 to the minus 3 or electron volts, it can get boosted to a giga electron volt energy. And so you should you predict that there are all these giga electron volts, photons which are coming to you. So around every TeV blazer, you should see a GeV halo of GeV photons. Turns out that several cases of nearby TeV blazers which people have looked at, and they've looked at with sufficient sensitivity, you don't see this halo of emission. Of course, this is an interesting thing. When you don't see, what do? You have to find a reason for this. All the calculations involve standard physics, so they think everything is pakka. Then these people, Naranov and Vok, who are the authors of this paper, came up with this interesting idea. Suppose there's a weak magnetic field in this void intergalactic medium regions. Then the electrons will be deflected in one direction. Positron will be deflected in the opposite direction because they have opposite charge. So these beam will get spread out. If they get spread out, the GeV emission will also get spread out. If you spread them out sufficiently, the surface brightness of the GeV halo that you see can drop below the detectability limit of your telescope. How much magnetic field do you need for this? It's about 10 to the minus 15, 16 Gauss. Femtogauss are even smaller. This is extremely small, much bigger, but by the way, than the seed fields that I was talking about for the battery. And this 10 to the minus 16 Gauss, if you work out the coherence length, this is if it is coherent on a megaparsec scale. If it's got smaller coherence length, because the electrons then will randomly walk in this angle of deflection, you need stronger fields to produce a coherent effect. Goes roughly a square root of the coherence length. So smaller the coherence length, stronger the field that you require. And this is in the voids because all this is happening. This E plus E minus pair conversion, the mean free path is tens of megaparsec. So it doesn't happen in regions which are rich in galaxies. It happens in regions we don't have any galaxies, so far away. So this observation, if it is true, it is remarkable. It means that there is some process which has filled the universe with what you think is weak fields, femtogauss, but it's not really weak field, and it's very difficult to explain from any other process. And that's where all the people who are doing primordial magnetic fields, before these observations came on board, suddenly got a lease of life because they could always refer to this and say, now we have to produce something from the early universe. So I won't go into all the other constraints. So what is one of the basic ideas? And there are a lot of people, including Sriram in the audience and Rajiv Jain in the audience. Rajiv gave a very nice talk earlier in the conference, who worked on this problem. Originally suggested by Mike Turner and Larry Vidro. And much more work done by Bharat Ratra and very nice review, very nice paper by Jerome Martin, who is in the SOC, and Yokoyama. Is maybe inflation. There was an epoch of the universe where there was an exponential expansion of the universe. This thought to have solved many problems associated with standard cosmology, including how to form structures like galaxies today. Most important problem that it could solve. If there is such an epoch, then in this epoch, even if you had charges before, it will all get diluted away. So you have really vacuum. And so there is no flux freezing kind of stuff that we are talking about earlier. Even though it's vacuum, the vacuum always has quantum fluctuations, which are called vacuum fluctuations. These vacuum fluctuations, they are stretched out, okay, because you have exponential expansion. So if you have a small wavelength vacuum fluctuation, which is produced on a causally connected region, they will get stretched out and they will typically get amplified. Now, this can happen for any field. It can in particular happen for an electromagnetic field. So you produce both electric and magnetic fields. Okay? Very long wavelength electric and magnetic fields. When the universe transits back from this inflationary era, into what is called the radiation dominated era by all the energy from what is called the inflaton transferring back to ordinary stuff, matter. Charge particles are produced. These charge particles will now short out electric fields because electric field charge particle, positive guys will move one way, negative guys will move the other way. And they will short out the electric field and freeze the magnetic field. So from a long wavelength electromagnetic wave, you go to just pure magnetic field. So this is an inflationary magnetogenesis scenario. Lots of problems. The basic problem is that unlike things which produce scalar perturbations and which later make galaxies and all that, magnetic field perturbations dilute even when there is no flux freezing. The radiation energy density, and people technically call it conformal invariance. You can map all the electromagnetic equations to what you will be applicable in a non-expanding universe, and then add the effect of expansion. And the expansion just dilutes away the strength of the magnetic field. So even if you produce a strong field initially, like any other field from this vacuum fluctuation, it goes to strength of about 10 to the minus 50 or 60 Gauss, unless you change your Maxwell's equations in some way. And so what people have done is to break this conformal invariance by coupling, for example, the inflaton, curvature, various things which Rajiv also talked about. Don't worry too much about it. Even if you do such arbitrary things, there are all kinds of problems associated with it. And I won't get into all the details of the problem. And I think, Sriram, I have 5 minutes or what?
Yeah, few minutes, Kandu.
Yeah. I mean, if you do various kinds of theories, you can produce, for example, about 10 to the minus 12 or 13 Gauss. You can produce fields which are helical by themselves. These fields could be on small enough scale that they produce gravitational wave backgrounds. All the work which I have done on this generation are all involving Seshadri and chelas of Seshadri in some way. So one of the very bright chelas of former students of Seshadri is Ramkishore Sharma, who is now a postdoc at Nordita, and he made gravitational wave predictions for this, which could be in principle detectable by the laser interferometric space antenna, LISA. Or if you make it at a very low energy, it could even be detectable by the pulsars timing array observations which are coming online. Okay, so we have made all kinds of calculations of this effect also. By the way, the shorting out also reminds me, I'll just I'll go to the conclusion thing. I've been talking about magnetic fields all the time. And a self-respecting physics student should be asking, what happened to electric fields? Okay, because you know that electromagnetism is not electric and magnetic fields separate, but if you run, you will suddenly find an electric field when you have a magnetic field or the other way around, right? You will have Lorentz transformations. But we have been talking about magnetic fields, and that's for a very, very simple reason. Our universe is got electric charges, but does not have magnetic charges. In fact, the strongest limit on what I call magnetic monopoles, magnetic charges, comes from the fact that our galaxy has a magnetic field. And if there are magnetic monopoles, magnetic charges which are free to move, then they would come, just like electric fields get shorted out if you have electric charges moving around, both positive and negative. Magnetic fields will get shorted. So our universe is very interesting. It has electric charges. It has both positive and negative electric charges, although it's electrically neutral. These charges in many contexts can freely move. So if you have a capacitor and I put both positive and negative charges will move to one end, positive will move to the other end. You will simply cancel out the charges in the capacitor plates and you'll get zero field. Okay? It will get discharged if you connect a wire to a capacitor which is charged, right? So that's why the electric field plays a subdominant role. Of course, if you ran fast enough, you will produce electric field. And that's the additional ingredient, that in most contexts, the velocities that we encounter in astrophysical systems are sub-relativistic. There are contexts like in black hole jets, pulsars, which are rapidly rotating, where the electric fields will play a very important role. The velocities can become relativistic in these jets. But in galaxies, in stars, in clusters of galaxies, in the Earth's interior, the velocities are all much smaller than the velocity of light. Velocity of light, 300,000 kilometers per second. The galaxy interstellar medium velocity is 10 kilometer random motion, 100 kilometers rotation per second. Cluster is 1,000 kilometers per second at the best. So these bunch of reasons make me talk about magnetizing the universe, not electrifying the universe. Okay? I hope I've given you a flavor that the universe is magnetized. And these fields are pretty strong, and you need cosmic batteries to provide you the first seed magnetic fields. These seed magnetic fields are not strong enough to explain directly the observed fields. You need dynamos to amplify and maintain the fields. By the way, even if you produce fields in the inflation, people think that, oh, then you will explain galactic fields. You will not, because you will explain the galactic field initially, but then the field will, Lorentz force will cause turbulence, will cause motion, will dissipate. You need to maintain it. So you always need a dynamo. They are not people who are fighting with each other. They can coexist with each other. Okay? You need dynamos to amplify and maintain the field. The coherence of the field, tens of kiloparsec, is the interesting thing in the galaxy. Tens of kiloparsec in the cluster. And this depends upon how dynamos saturate. And this is an intrinsically nonlinear problem, because it's a V cross B. The V is an independent variable. The magnetic field is an independent variable. And so you have a coupling between these. There are two equations. There's a nonlinear bunch of equations. You try to do, and it's stochastic because the velocity field is random. So you try to do simple theoretical models. You're always limited by the theory that you can build up. You try to do simulations, you're limited by the resolution of the computing power that you have. So it's a very interesting, still open problem with lots of interesting ideas to look at. And if you really detect and confirm that there is a primordial magnetic field in the intergalactic medium voids, then it's very likely that the early universe had a strong role to play. Now, I've talked about traditional probes like the radio astronomy, optical astronomy, infrared astronomy, which are all providing probes of the magnetic universe. But over the last decade, gamma ray astronomy has come into prominence with these blazars and even earlier suggestions about cosmic ray particle. And of course, now the fashion is gravitational wave astronomy, and the stochastic gravitational wave background that could be produced by various effects, including early universe magnetization. So thank you very much for your patience and attention. I hope I've given you a flavor of the subject, although not covered all the details I was planning to cover. Thank you very much.
Thank you. Thank you very much, Kandu. I see a couple of hands raised. I will come to those. There have been questions from some students. So I'll just, raise some of the simpler ones first. First is, does the interstellar magnetic field affect the light from faraway stars or supernovae?
The interstellar magnetic field doesn't directly affect the light. But the interstellar magnetic field, for example, one of the ways in which you probe the magnetic field is if you have dust grains, which are elongated and charged, then they are rotating and they rotate about the field direct with the minor axis. If the field is pointing this way, then the minor axis of this dust grain is aligned with that, and they're rotating. And then if you scatter off those dust grains, or if those dust grains emit radiation, then Of course, the light, you get an extra effect of the starlight being scattered of that and being polarized by that. Otherwise, it doesn't directly affect the photon. The only time context in which I said is the TeV photon directly interacting with the starlight and converting into pairs. For that, you need very high energy photons.
Okay, thank you, Kandu. There's another question. What is magnetic Reynolds number? How does it differ from Reynolds number in viscous fluids?
Sorry, I didn't have time to dwell on that, but it's a good question. Thanks. Where was that? Yep, here. So the Reynolds number in viscous flows is a ratio of the velocity times the length scale divided by the kinematic viscosity. The Reynolds number, the magnetic Reynolds number, you replace the kinematic viscosity by the resistivity. That's the only difference. The reason is from this equation. There's an inductive effect due to V cross B. There's a dissipative effect. This J got replaced by Ampere's law to curl of B. And so there's a resistive term. You ask, what is the ratio of this term to this term? The B cancels. I'm just making order of magnitude estimate. There's a V here, there's a eta here, there's a 1 over L here, length scale. And so you get another dimensionless number. The length which was in the denominator goes to the top, and eta comes to the bottom. The reason why the magnetic Reynolds number is so large, like the fluid Reynolds number, is that all these transport coefficients is basically some velocity times some length scale. That length scale is usually small, but these astrophysical length scales are very large. And so the ratios are always large. So that's very closely related to the fluid Reynolds number.
So there is another question which asks, what is a stochastic field?
Okay, sorry. So what I meant is that, suppose, what is a stochastic variable? Suppose you have X and you say that's a stochastic variable. What it means is that it doesn't have a deterministic value. It has a probability of having some value. So there's a probability distribution. So stochastic field is exactly that, except that the probability distribution, it's a variable which varies with position. For example, the velocity field or the magnetic field, which also depends on position, but it's also random with some probability distribution. So that's the sense in which I'm using a stochastic velocity field or a stochastic magnetic field.
Thank you, Kandu. There is another question which asks, did primordial magnetic fields appear simultaneously with the production of gravitational waves?
Yes, I mean, they can, in the sense that gravitational waves, of course, they can arise from this vacuum fluctuations of the metric tensor. And in fact, during inflation, you have an inflationary generation of gravitational waves from the same kind of quantum fluctuation which led to scalar perturbations and structures. You have metric fluctuation which will lead to gravitational waves. Over and above that, as you're generating magnetic fields, you have extra energy momentum due to the electromagnetic fields, which could be anisotropic, which are anisotropic. So this can also source gravitational waves. The gravitational waves which we calculated are not directly coming from the inflationary era, but they're coming, they're being sourced as the field itself is being generated. In fact, they're exactly those, which are, I think, I have to learn to go forward in life and backward. These things are exactly those which Ramkishore calculated, are coming from the, this is some electric field contribution, this is the magnetic field contribution, before reheating of the universe, this is after reheating, they're coming from that. But they're coming from, if you take Einstein equation, there's a right-hand side to that Einstein's equation, which is the anisotropic stress, which can source gravitational waves. They're coming from that. Yes, so you can generate simultaneously both.
Okay, there are a few questions, a few people who have raised hands. Rajiv, unmute and ask your question.
Hi, Kandu. Can you hear me?
Rajiv, nice.
Hi, Kandu. Very, very nice talk. I learned a lot.
You will know all this stuff.
No. So you mentioned about this battery, the Biermann battery mechanism. It essentially can generate initial field from zero initial conditions, and then can also amplify it further.
Right.
So I wanted to ask about your opinion of this. Again, the initial fields being generated from the second order perturbation theory.
Yes.
You know that you can generate vorticity
compared to this Biermann battery.
Right. So whether there has been an improvement, because I know of some older results, which are again very weak, whether there has been any progress on that front, and how does it compare with the typical Biermann battery?
Smaller than this. They're much smaller than this.
I see.
I mean, during recombination, you can generate from second order perturbations. I think the Japanese group calculated Ikichi and all that. That was 10 to the minus 30 or something.
Yeah, 28 or 30. Yeah.
And then later there was some other calculation. Even Ramesh Narayan and all calculated something. They are much smaller than this.
Okay, so it's like not such a useful mechanism to look at the.
You know, of course, I should qualify this statement, because here question is what is generic. There, of course, you will get something, and anything is okay. Okay. In fact, once one of my friends, who you may know, Vivekanand, to say that I'm trying to generate weaker and weaker fields all the time. So everything is useful. This structure formation shocks will happen absolutely generically, because even if the thing was collision-less, you will generate these shocks, small-scale electric magnetic fields, and then they will lead to coherent fields. The Biermann battery itself requires reionization, right? Reionization requires stars or quasars. Those guys to work may require its own magnetic field, but that can be generated internally by smaller-scale Biermann batteries.
I see.
But the good thing about these battery processes is they automatically generate coherent fields. Because what you have here is these gradients are all correlated on the scale of the galaxy or on the scale of the ionization fronts and all that. So they automatically lead to very coherent megaparsec scale fields. Unfortunately, they won't lead to femtogas.
Yeah.
They are still in business, but you know, there's this whole Chang Broderick from a group which said all the Blazer stuff can be explained by plasma instabilities.
Okay. And the second one is
Rajiv, very briefly, Rajiv.
Yeah, the second one is just a comment. So towards the very end, you said that the intergalactic magnetic fields can only likely be generated by the inflationary magnetic fields because of the very large.
I didn't say that. If I said that, I'm wrong.
So I just wanted to sort of get a clear understanding of that statement, whether one should continue to work on inflationary magnetogenesis or not.
Oh yes, of course, we should continue to work on anything.
Yeah. So, but then my other question was that are there other possibilities which can then generate such a large coherent, although very weak magnetic field in the intergalactic medium?
Yeah, you see, people talk about phase transitions, right? The other universe stuff. So you have, let's say, QCD or electroweak phase transitions. There are two problems. One is present theory of either the QCD transition or the electroweak in the standard model are what are called crossover transitions. They're not first order phase transitions. So they don't occur by bubbles being created and expanding and doing all kinds of stuff. In a crossover, everything happens continuously, the phase transition. So they're not great. I mean, of course, Tanmay Vachaspati has his own various other ways of doing this. So there's that whole other thing. They will generate smaller scale fields, very difficult to calculate properly. But then the decay of these fields, if they're strong enough, and especially if they're density, can lead to larger and larger coherent scales. So I wouldn't rule it out. In fact, it looks to me that inflation is always more difficult because of all the problems that you know of.
Yeah.
Okay. Once I asked, I think once I told all these stories with age.
So,
I asked, I think Colby to us, have you thought about inflationary generation of magnetic field? So he said, yeah, every time I'm taking a shower. So Rajiv, we should still think about it every time we take a shower.
Okay.
so
Thank you so much,
yeah,
Kandu.
thank you, Rajiv. We'll move on to the next question. Devinder, can you unmute and ask your question?
Sir, my question is that what is the total magnetic and electric field of universe?
What is the total?
Energy density of magnetic and
of
electric
universe.
fields in the universe.
And if zero, then why, sir?
No, wait. It's may not be zero, right? I mean, you see magnetic fields everywhere, so it's not zero, of course. If I take let's start from the cosmic microwave background as a reference frame. If I take the energy density in the cosmic microwave background radiation and convert that completely into magnetic field, then you get a field of 3 microgauss. Okay. And in fact, this was the coincidence which Hoyle noticed, that if I take the energy density in the cosmic microwave background radiation, the stellar turbulence, cosmic rays, everything is comparable, and he thought this was too much. And so he always try to produce it locally.
Okay. Thank you, Devinder, for your question. Atri, can you unmute and ask your question? Atri, can you unmute and ask the question? Okay, Atri seems away possibly. Lakshmikant Tiwari, can you unmute and ask the question, please?
Actually, by mistake, I think the hand is raised.
Okay. All right. No issues. Dr. Lakshmikant Tiwari, are you around? Can you unmute and ask the question? Okay.
Sir, really, sir, it was very nice talk. No questions, sir, on our side.
Okay, thank you. Devjit, a brief question. Unmute and ask the question.
Sir, my question is there any relation between entropy with this magnetic field in this in your discussion?
Entropy.
Yes, sir.
I mean, see, of course, entropy, complicated stuff. Yes. I'm thinking about only energy density of the magnetic field. I'm not thinking about the entropy. Of course, if you have microwave background radiation, there is maximal entropy. But if you have ordered stuff, maybe you can have a measure of entropy. If you have turbulence, you can have a measure of entropy. But I'm not at all worrying about entropy associated with the magnetic field.
Okay, sir. Thank you, sir.
Thank you, Kandu. That covers all the questions that we had. Thank you very much for your talk. We greatly appreciate you joining us and giving this lecture today. And thanks everyone for joining. Oh, I'm sorry, there is one question from the panelists. Sagarika, unmute and speak, please.
Hi, Kandu. I have a question. So you said the helicity is introduced when a galaxy rotates up or down. So it is in order to conserve the angular momentum. So how will we physically picturize it during inflation? How we helicity
Inflation doesn't do this. Sorry, I mean, I may have given you the wrong impression. This was only for all these astro systems like our galaxy, the sun, rotating stuff, rotating stratified medium. Inflation, I think Rajiv was talking about it today. It's all whether you have something which kind of breaks parity. I mean, for example, axions coupling to FF star. Where is that?
Yes. In the action, we introduce a parity violating.
No, this term here, theta FF star.
Yes, I was just asking how to can we physically interpret it somehow? Like
No, I mean, the only thing which I know is that if you write down the equations, and if you have a particular sign for this term, then one of the helical modes will get amplified much more than the other. In fact, I think I had a picture of that from Ramkishore's work, that like here the red one is positive, blue one is negative helicity, and sorry, the solid line is negative and this dashed line is 0. Okay, so you can see that the red and the thing, I mean, it just depends upon, once you have a parity breaking term in the action, you have a parity breaking term in the equations.
Okay.
When you're amplifying something, one parity gets amplified more than the other parity.
Yes, yes.
That's all. I don't think it has anything to do with motions.
Okay, it's just we need to introduce the term back.
Yeah, you will know more.
Okay. Thank you. Thank you very much, Kandu, for joining us and giving this talk. We appreciate it. Yeah. And I will see you at the session later.
Yeah, thank you very much, and all the best for your center and your conference and everything else. And I'm sorry I overshot a bit. But
No, not an issue at all. There were people waiting to ask your question. Thank you very much, Kandu.
thanks a lot. Bye.
Thanks everyone for joining. Good evening, everyone.